Welcome back. This is the last talk of the afternoon in this theater. After this talk is finished at 4 o'clock, we'll have the lightning talks in the big theater, Theater 5. They should be quite exciting. And now I'd like to turn it over to Mohit Sidana and Tom Burgmans to tell you, well, testing vectors. I think I can figure that out.
Yeah, so good afternoon, everyone. My name is Mohit Sidana, working as a search architect for Wolters Kluwer, where together with my colleague Tom Burgman, we're working in a search team focusing on development of a very matured keyword search functionality. And I'd like to ask maybe Tom also to introduce himself.
Yeah, my name is Tom Burgmans, technology product owner and team lead of the search team.
Yeah, so a bit more about Wolters Kluwer. So if you're not familiar, Wolters Kluwer is a company where we provide access to the information to the professionals in different domains like tax, legal, healthcare, compliance, by offering many online solutions. And in these solutions, we offer access to millions of documents where our users can perform full text search, doing their research and finding the information they need to fulfill the needs of their end users. So a bit of introduction. What we would like to talk about today is our journey, where we would like to discuss our learnings by applying series of experiments where we conducted tests to test the capabilities of vector search while maintaining our keyword search functionalities as it is. As we all know, vector search is the game changer because it's in the field of information retrieval. It not only allows for searching for keywords, but actual meaning, unlocking different use cases. So we see more and more how users are searching for the information and how they're consuming that information is ever changing. Looking at this very beautiful picture, it's actually a very famous way of summarizing it's called Gartner Hype Cycle, which is a graph which summarizes the 5 stages of a new innovation, from the innovation to the hype, and then it looks like it's a silver bullet which will solve all the problems. But as we know, you go through a phase of disappointment where it doesn't deliver, and then from there the understanding and widespread adoption of that. So why is large-scale testing is very crucial? Because firstly, in real-world applications, we are dealing with massive data sets. So we have millions of documents which should be converted to vectors, but also at the same time finding a balance between the quality. So we saw an earlier talk where we talked about vector search is a really cool, but when you talk about search, you also expect other features to be part of it, like spell checking, facets, filtering. But at the same time, also maintaining a balance because it can really blow up your costs, because vector search is expensive in terms of time and the money you spend on it. So we divided this task into actually 2 parts. The first part is, given a piece of text, you have a model which you can use to convert those text to compute the embeddings. And from our initial research, when we started with these experiments, this is one of the things which came up a lot, that in doing computing embeddings and inference is the pain point because it just doesn't scale. But also doing the actual ANN search, which I think which my colleague Tom is going to talk more about in detail. So I'm going to focus on this part, computing embeddings. So what we did, we started with experiments, our experiments where we took variable lengths of text, 1,000 queries, different lengths, but also 4 open source models with different dimensions, call it small, medium, large. And we developed an inferencing service where you give it a piece of a text and then it computes the vectors. And while we did that, we actually tested this with 100 threads. So that was our baseline. A small disclaimer, we are part of the production team, so we are not machine learning engineers. So when we started with the journey, we started with a very naive approach that we didn't know much about vector search or computing embeddings. So this graph is a little bit funny one because you don't see those first rows because they were very small. We didn't have a time to fix it here, but this was the first slide we want to talk about. When we started testing testing the query inferencing part, we wanted to know what kind of machine do you really need to run that inferencing service. So we started with deploying our services to the regular CPU machines, but we also soon found out that they will not scale up. And GPU, so we also tested those on GPU machines, and we also looked at these special chips which are called advanced vector instructions. It's a special type of instruction sets which are optimized for only CPU. What we found out that in order to do inference or compute embeddings, GPU was the clear winner. And because when we really tested this with 100 threads, those graphs, as you can see, the query latencies were really, really high, especially with larger models. And this was one of the learnings so in order to do inferencing, you need really GPU power. The second test we did actually is what is the correlation between the text length and the embedding inference latency itself. So if you look at the graphs, you can see the very tiny peaks where we tested it also with 4 models. So computing embeddings with different dimensions. And what we also found here is that those larger models where we're computing thousands of embeddings, so in this case 1024, putting a load on the system and with more number of tokens, they really the latencies grow very exponentially. So this is because those larger models are computing vectors for each of the tokens, and then this was one of the very nice learning because you have to do this not only at query time but also at index time. So you have to chunk your text into sections and then use that for computing the embeddings. This is a slide, it is a common knowledge, but we included it here. So how this will perform if we put a lot of load on the system. So we tested with 100 threads, but we also tested our services, the inferencing part, with more and more concurrent users, so all the way to 800. And this what we learned here is that the high number of thread, how much it impacts the embedding calculations, especially with those large models. So going to the next slide, and while we were doing this research, we also learned along the way use ONNX. So ONNX stands for Open Neural Network Exchange. It's a format which you can convert your models, and this was a great performance booster, especially on, we used the special runtime for this, so ONNX with GPU, and this was a clear winner that doing inferencing with ONNX and GPU, the query latencies were under 50 milliseconds for those 100 threads. We are not done yet, so we're still exploring this very exciting domain. And there are some other things we are currently working on. For example, converting models to ONNX was really a game changer for us, but also applying more optimizations to the model. So applying like constant folding or quantization. So from our earlier tests, using those floats can be very heavy on performance. So from there, if you go to int, it was really like 50% better than what we saw with our first test, but also scaling out the embedding service. So we tested it with 800 threads, but with only one server. But can we also just test this by scaling horizontally or vertically, and use that knowledge to implement a solution which can be deployed to production. So once we had the embeddings, we could just go and use our choice of search engine. We have been using Solr for a number of years, and Tom is going to talk about how we tested ANN search.
Yes. All right. I'm going to show even more numbers and more graphs. And I realize it's the last full talk of the day, so I try to do my best to keep it very interesting. Right. So yeah, we have these two sides of vector search. One is the inference side we talked about, and now I'm going to talk about ANN search. So that's what happened after we got the vector from the inference side. So yeah, vector search is a different thing than keyword search, than searching an inverted index. Inverted index is a table, look up words, and then find documents that belong to each word. But vector search is traversing a graph, and that works very differently. The laws of physics works just differently for vector search. It's literally hopping from one node to another node to find a spot in that graph that is most closest to the vector of the query. And that's, yeah, we just want to try to find out what are the parameters, what makes this fast and what makes it slow, right? We try to learn everything about it. So let's go to that journey. First, this is our situation, our defaults in the test that we want to conduct. Index 2.6 million documents. Index this in a fairly large machine of 128 gigabytes of memory, so just to make sure that the whole index fits in it. Also use 100 concurrent users to pound the system with queries. In between the calls, there's 1 second of pause. So it means that we have 100 QPS at maximum, which is kind of close to the to a busy day on one of our major products, right? So we choose that deliberately. Also interesting to say, we made sure that every query that a thread executes is a unique vector. Just to make sure that we are not testing the cache, but we are testing real performance of the calculation. And use 4 different models for that. And for the rest, I can say we just took the Solr defaults that are there as a default, right? But we're going to vary with each of these parameters there too. So the first lessons learned, and it's a very important one, is that to realize that a Lucene index is built of segments. And segments are there for a good reason. So segments are there in the Lucene index to make sure that whenever you got new content or updates, you got them quickly available. And at the same time, a segment is immutable, so it makes sure that the index is very stable and doesn't get corrupt. But there appears to be a problem for vector search. Each of those segments are their own HNSW graph. And I have the strong impression that if you do this in Solr, the current search, it searches them in sequence, which means that it takes a lot of time before we got results. Right? I was kind of underwhelmed with the test results when I was doing those tests, and I went to the Slack channel, relevance check Slack channel, start talking about it, and somebody suggested to me, did you ever thought about merging your segments? I never thought about it. Right? It was never a concern in keyword search world. We just went with the Solr defaults. But anyway, I did it. I just did a forced optimize. Got 1 segment. It took a lot of time, but it made a whole lot of difference. And even to an amount that my search latencies got down, but yeah, 10 times quicker search results. So I had to throw away all my test results so far and start over again. And that was the bad news. The good news is at least I got something which is way quicker, knowing that a forced optimize is not something that you would ideally want to have in a production system where you get constant updates. So yeah, it requires to think about a merging strategy again which maybe you took for granted on a keyword search situation, but since it's now vector search and it appears to be very sensitive to segments, merging has to happen in some way. So that's what the title basically says, get your segments together. Right? So, with that lesson learned, for the rest of the test I did it all with fully optimized indexes. So, okay, if we index a piece of content, right, a set of content, how does that have an impact on the size of the index? And this is what the first graph will show you. Those 2.6 million documents indexed without any vectorization is about 7 gigabytes big. But the moment we start to vectorize the abstract, which we indexed Medline content, which contains metadata and abstract, we vectorize the abstract with different models, and you can really see the impact of just doing that, how big that index grows. So a vector is a large piece of metadata that you have to index, and it could even double the index size. And also the index speed will go up if you vectorize content. So that's expected, I think, but now we know how much it will differ, especially for that content set. On the query side, actually were pretty good results. So these are latency numbers, and we see milliseconds there. And for a content set of several million documents, we got very low latencies with the default parameters that we took for our stress test. There are a couple of spikes there with the 10 million documents, but that is not because of the 10 million, I guess, but it is because of those tests were done when there were 3 segments instead of 1. So, with this amount of volume, with these parameters, test results are pretty okay. But we are not done yet. So, knowing that we could handle that amount of content, I created a couple of collections with varying content sets and start just querying multiple collections at the same time, just to see how that behaves. And you can see below the amount, the combined size of all those collections that were queried simultaneously with the amount of users of threads. And still very good results. Even on the very right, we see there are 50 million documents queried at the same time with 300 users. Very good results. With one exception there, and there's this one big spike. This was a combination of collections that together took more than 128 gigabytes big in content size, or in index size. So, and then suddenly we got the latencies go through the roof. So there is a big lesson learned here. Make really sure that if you have a vector index that it all fits into memory, because the moment it doesn't, then you get this enormous spike in latencies there. Going on to the k-value. So k-value is something that you have to specify at query time, which indicates how many results you would like to get back from a vector query. Important to know is that k-value is not just the number. K-value is also a relevancy driver. Because the higher you make k, the more likely it will be that the best documents appear in the top 10 of your search results, or the top X. So it makes sense to increase the k-value just to make sure that your very top vector search results are of better quality. And in that sense, it is just interesting to know how far can we stretch k until we got into problems. Right? And of course, the expectation is the higher the k we make, the more work it has to do. So probably latencies will go up. And that's indeed what we saw here. So here we see the test results for each model. You see the test results there with increasing values of k. So for all models, it goes pretty fine, up to k of 1000. But the moment you get multiple thousands, then you got into the problem spaces there. Of course, it depends on your use case, if it's acceptable or not. Going on to similarity function, there is also something you can vary with. So our search engine that we tested supports 3 different kind of calculations to measure vectors with each other: Euclidean, cosine, and dot product. Euclidean is the distance between vectors. Cosine measures the angle between vectors, and the dot product is a mix of both. And if you look at the just the calculation, the actual formula for calculating each of these similarities, then you would expect, just based on the complexity of a calculation, that our product is the easy one. It's the most performing one, just because it's the most simple calculation that you have to make. And that cosine would be the least performing one. So that's expectation, and these are test results. And indeed, so here you can see each color, each function gets its own color. And indeed, dot product appears to be the most performing way of calculating vectors with each other. That's expected. Now the interesting part here, that cosine is indeed the least performing one, but only for low k values. Right? The moment that we got to high k values, like around 3000, then you suddenly see that Euclidean gets more expensive. And why is that? I have no no idea. So if somebody knows, please let me know. I have no idea why k value would be of any impact on the calculation of a vector, and why that would be different. But that was probably a good explanation, because it looks like there's a very, let's say, consistent pattern that we see. Yeah, it's not just a coincidence. All right, vector encoding. So by default, a vector is a bunch of floats. That's the default way of representing a vector. But Lucene supports two ways of encoding a vector: as a float, which occupies 4 bytes, or as a byte, which occupies 1 byte. And we just like to know, okay, one or the other, what does the impact have on the content size, the index size, and also the query latency. By the way, you can change a float vector into a byte vector, and if you do that, it's called scalar quantization. You have to be careful about how you're going to use that byte vector. So it depends on the similarity function that you're going to use, what the correct way is of quantizing that vector. Do you want to maintain the angle, in case you would like to use cosine similarity, or do you want to contain the relative distance? And in that way, another way of quantization needs to happen. So that is a side note. We took the angle approach because it's the simpler one. But yeah, I mean, that's something to keep in mind once you start doing that. So the expectation is that if we change a float vector into a byte vector, do that both on query side and on the content side, that at least the index size would go down, but also it may probably have a positive effect on the latencies, because it may be much easier to calculate with a simpler vector representation like that. So first the index size, and indeed, yes, index size goes down. Not like 4 times down, which you may want to expect if you change something from 4 bytes to 1 byte, but at least for the larger vectors we see half of the index size that we had before. Right? We have float on the left and byte on the right. The index speed, not so much difference over there. The query side, also there, it makes indeed sense to quantize your vectors into the byte variant, because their latencies goes down as well. Of course, if you do this, it comes with precision loss. So it's not just we're training here relevancy against speed, but that's like always. The moment you make decisions, we have to balance somewhere in this triangle of speed versus cost versus relevancy. Okay, I'm going to talk about a stress test. So this is about, okay, let's just increase the amount of threads, the amount of users, and then see where the system starts to crack. So how many concurrent users can we let the system handle? Also here, there's a distinction between a float and a byte, because we already thought, well, if you put index vectors as bytes, it will probably be able to handle more stress than if it would be just floats. And that is indeed exactly what we see here. So, and also the small models can handle larger load than the big models. So on the x-axis we see here the amount of users that we concurrently let the system handle. And yeah, this is pretty good, because at least for us, the stress that we usually see on the system is about like 400 users at the same time making queries each second. And here we can see it already goes to the thousands, and we still got pretty good results. So that's an encouraging graph, at least. So I'm going on to filtering, and this is really where you can see how vector search is different compared to inverted index search. Filtering means that the moment that you actually say, well, a subset of our content is not accessible, it means that in this graph, the HNSW graph, you create nodes that are dead-end roads. So you make the graph less traversable by applying a filter. And it means that the expectation is that the moment you add a filter to a vector search query, that latencies would go up. And that's exactly the opposite of what you have with inverted index. You apply a filter there, then usually gets a faster result. Now, how much does a filter impact vector search? And that's what we wanted to test, and we have some very interesting observations there. And here you can see, indeed, the moment that we add filters, especially if you start to narrow the scope more down, so from left to right, we got a more narrow scope, you see latencies go up. And for the small models, it kind of stays within acceptable ranges there. But the moment we have some models there, especially the one on the very right, we see it got some very problematic search results suddenly. So Houston, we got a problem. If you make the scope very narrow, then latencies go up again. Well, go down, I mean. So we got good performance there. And this is because there is a feature in Lucene that switches from graph search to brute force KNN search the moment that the filter is so narrow that it passes some kind of a threshold. So we see clearly that feature here in action, but there is this bandwidth, some problem area there in the middle, where you can see, well, that is kind of between 1 and 5% of the search results, in our case at least. We see there are very high latencies. So we need to find a fix for that. And by the way, if you look closely to that yellow area there, we got two filter situations that got basically the same amount of results back. But one filter performs poorly and the other one does relatively okay. What's going on there? First, that was a real head scratcher. I had no idea. But then I started to see one particular thing, is that the problem filter on the left here had only one term in the query, while the performing one had multiple terms in the query. So it's not a coincidence. I got multiple cases where the one-term filter performed way poorer than the multi-term filter. I have also no idea why is that the case, but I have a theory at least, is that the one-term filter, those documents that passes the filter appear close to each other in that graph, in the HNSW graph, and therefore the blind spot around it is also bigger. Well, on the right side you see the results are more distributed across the graph, and probably in that situation this graph is better traversable than this graph, although there's the same amount of documents that are actually allowed to pass the filter. How true is this? I have no idea, but this sounds plausible to me, and there's so far nobody yet that said the opposite. So I asked this question in the Slack channel too. But yeah, so we had still that problem that for some filters, this one-term filter is something that can happen. A user can just select it. So we need to find a way in order to bring down the latency for that filter. And maybe the next thing that we're going to try is a possible solution. So this is the HNSW max connections parameter, also called mmax or m sometimes. And what this specifies is the amount of connections that each node can have to other nodes in the graph. And the idea is that, well, if I increase the amount of connections there, then probably that makes the graph better traversable, especially if you apply a filter there. Also, it comes with a cost. It takes longer to index. And I thought if we would do that, it would probably also increase the index size. Now, about that last one, we got a very interesting result that it appears to be that's totally not the case. Right? So I increased the amount of connections, but for some reason, it does not impact at all the index size. So what's going on there? Again, I have no idea. Right? I've got a lot of questions in this test result. could it be that this parameter is not working at all? Or could it be that maybe in Solar or Lucene there's just a fixed amount of bytes reserved for the amount of connections, and therefore we don't see we don't see it here? Again, if somebody knows, please tell me. So yeah, the index speed. I mean, we see a bit of an uptick there, not so much. But did it work on the query side? So did it really solve our filter problem? And it looks like maybe. The answer is yes, but it's a maybe here. You know, on the right side, we see some problem filters there which have very high latencies, and then I started to increase the M factor, right? From 16, which is the default, to 32 to 46, 64. And yes, if I create higher values, then latencies go down, but they don't go down with higher increases of the M value. So I'm not really sure if that actually was the fix. Right? It could be that maybe every time we build up a new index, there's always randomness involved, and we recreated the index a lot of times. And that randomness is maybe the reason why in the first try we got those very high latencies and later we didn't get them. Maybe it was the M factor. Right, so I cannot, and also on the other, for the other models, I really couldn't see that it actually did increase the latencies there. So not always, at least. So this is a bit of a question mark. Probably requires more testing to get more concrete answers there. The other query side, the other index side parameter is HNS beam width, also called EF construction with other search engines, and this is the candidate list that is that the engine keeps whenever it inserts new documents inside the graph. And the candidate list basically is a list of candidates where potentially this new document could make connections to. So the reason for increasing this size is that it has a better chance in order to connect to the correct documents. And the smaller the size is, the faster indexing will happen. That's the expectation, at least. Though the lesser quality you would get in the construction of that graph. So in other words, it does not really do anything with query latency as expected, but it may have some impact on index speed and relevancy. But the relevancy side we didn't test. Not yet, at least. Right, so indeed, the index size is not affected by a changing value. The index speed, however, is impacted. So with a higher value of EF search, or EF construction, I mean, we got higher index times, but also with a lower value than the default 100. And why is that? I would expect that to be lower. I mean, if you have a shorter list, it would make it faster to index new documents, which is not the observation that we had. So again, a question mark and no answer. I'm sorry. So on the query side, no impact. These are all very low latencies, and this variation doesn't mean anything with those low numbers. So yeah, so that's in summary what we did in terms of testing ANN search. And the next slide is a bit of a dangerous one. It's a wish list, and if you put a wish list in front of an open source community, you get reactions back like, index a pull request and then we talk. But with the risk of getting all kind of reactions like that, I'm doing it anyway. So a wish list that we have is, well, wouldn't it be nice if there would be no segmented index for at least the H and the W graph, because we can see at least the poor performance. Or maybe there's another way. We saw that there are some latest developments in Lucene and Elasticsearch. I've seen it as well, where those segments are being searched in parallel rather than in sequence, which can also already be a big help. And maybe that, I hope at least, that in Solar we also get this kind of development soon. So the other thing is to have the embedding inferencing internal. So we did it on the side, learned some lessons from there, but wouldn't it be nice if this was somehow part of the engine itself, so you don't have to take care of that externally. Internal vector quantization, we did a very brute force, simple way of quantizing our vectors and also maintaining the angle. The moment you want to maintain the distance, it requires a much more complex way of scalar quantization. wouldn't it be nice if the search engine was able to just take care of that as some kind of a post-processing exercise? A friendly way of hybrid search report. It's not part of the test, and I didn't tell about it, but to have hybrid search in Solr, it is possible, but it requires big, complex structures of queries. And we've seen other Lucene-based search engines already making a much more friendly, developer-friendly approach towards that. And the last part is multi-field vector fields. Now we have to chop up the documents in order to create vectors for those chunks. But if we have this, and I know there have been talks about that before, that this is maybe something that could be coming, then you don't need to chop up the documents. You can just have multiple vectors stored in the same document. So that's a wish list. It would be nice, but one can only dream. So, all right. This concludes our talk, and there's some time for questions. Thank you very much.
And since we have such a wealth of them from the Zoom, we'll start with the Zoom. Alexandra Feinberg, is Onyx also better on CPU?
Take that one.
Yeah, I think from our earlier tests, I think we didn't find that, but we did some early tests and we saw a significant improvement if you're using ONNX and quantize your models. So we did the int8 quantization, and we found the results were really better than what we were getting with the regular CPU.
Great talk. I have an answer to most of your questions, but I won't answer them here. We can talk later.
Good.
But I have a question myself. What JVM were you using? And do you know if Solr is enabling the Panama vector module for SIMD calculations?
For the JVM, we were using Java 11.
I think so.
Oh, if you're using Java 11, then...
Yeah, it may be on the slide, but I think it's Java 11.
Aruna Govindaraju, what is your approach to generate the byte quantized vector? And you can punt on that if it's complex.
Lucene will do that for you.
So the question was to byte quantized vector?
How did you do your byte quantization?
Okay. Yeah, that was a brute force way, as I said before. So first, we normalized the vector to a standard value between 0 and 1. And that was just, we still got a float back then. And then the second step was to turn that map that into a value between minus 127 and plus 127. So it was this two-step approach. It was, I think, 4 lines of Python code. Not ideal, I must say. So, but 99.99% of the vectors were still valid afterwards. There was a very tiny percentage which was not. But at least I did some hands-on, some sample experiments to see if at least I was still able to compare vectors and still got the same search results, which is relatively what we saw. Yeah. So only using cosine similarity. That said, I know it's not ideal. We have to, if we want to do this for real into production, we probably have to go to more sophisticated ways.
Thanks for the great talk, guys. I was really impressed with the results I saw from ONNX. Can you tell me about the level of effort it took to implement that and how you went about it?
In terms of effort, I think we use a lot of open source libraries and open source models. All the models we used for this talk was open source, available on Hugging Face, and we use Optimum to convert our models to ONNX. So in terms of effort, it was really not too much, because the Optimum library we use comes with a lot of support with converting models to ONNX and even applying further optimizations. For example, one of the tests we did, we didn't share we didn't have a slide for it, to convert the model and then optimize it for the AVX512 VNNI processor, which is just like a 1 line of Python code.
Kevin Liang, from an infrastructure perspective, how do you simulate concurrent users? Multiple threads, multiple pods, machines?
This was just a JMeter setting. where you can just say how many threads, concurrent threads, you would like the system to generate. So it is just like that. Right? We had a separate JMeter engine, EC2 setup, where it just runs and it simulates that amount of traffic.
Have you guys put any research into the text embedding inference by Hugging Face? I can take a Solvo.
Well, for these experiments, we haven't looked at it yet.
Oh,
But
okay.
yeah.
Thank you.
As we were doing this research, we were also learning more and more about how to really use these models and optimize it. And then every day you go to a LinkedIn post, there are like 100 ways to do it. So we just found the most optimum way. What we found we could have done, and then use that. But there are still a lot of open areas where we can look into it.
Habib Shopiju says, +1 for optimum. I had some issues setting up dependencies, but was simple from that point on. And also wants to know, was any comparison done on the quality of results for byte compared to float 32?
A short answer, no. No. Yeah, so we showed, Mohit showed in the beginning that triangle and then circle around speed. But of course, if you want to know everything, you have to also pay attention to the quality aspect of it. You're constantly making trades-off between cost, speed, and quality, with vector search especially. And this exercise zoomed and focused totally on speed aspect. So we have enough material, hopefully next time, for another talk. Right? And then we focus on quality.
All right, there are no more questions. Let's thank our speakers.
That's good.